approach.
Should I start from beginning or how is it?
You can just continue.
Okay, okay. I'm apart from other things, I'm supervising the seminars in our group, and I know that it's a difficult task, especially if you're both online and in the auditorium. So returning to the scales, if you look into them, you will see that all the scales are not only different, they are qualitatively different. For example, when I was a student, I liked to drill my teachers with the question whether the world is continuous or discrete, because we know both, and we know that the world is basically empty with the concentrations of masses in the points, and we know that the world is basically continuous as described by the equations of hydrodynamics. So the question is how to organize the mathematically strict and physically reasonable transition between the different scales. And what I mean, intuitively, it is clear that there should be such a transition, that we do some operation in mind when we transit from, for example, from molecules to hydrodynamics, or from hydrodynamics in a single pore to hydrodynamics on the level of billions of pores in porous media. But until now, and at least for me, this procedure, this mathematical procedure, was not fully clear. And this is what I tried to outline in this work. If you look into standard books or standard textbooks on averaging or on the scale transition, then you will see that most of them are basically related to the two simple operations. It is simple averaging over the volume. Consider, for example, some density M. For simplicity, today I will talk only about one dimension. Generalization on multiple dimensions is possible, but I will not touch it. So if we want to know average density on a coarser scale, you have to integrate it over the volume taken around the central point and multiply by 1 divided by volume. And this is a standard averaging. It's called volume average theory, which is based on such averaging. And it is pretty well developed in hydrodynamics and in transport and porous media, starting from the works. I think the first works were published around 50s or 60s of the previous century. If we make it a little bit more complicated, then we introduce weights of the different points. This is what is called weight averaging. So we select some volume, we call it support, and then we introduce weights of the different points. So we, for example, say that the points which are closer to the center of the volume are more important than the points are at some distance from the volume. And then we introduce the weight of each point. Of course, this weight should be normalized to 1, to unity, and then we take average with this weight, which is actually the mathematical operation of convolution. For the future discussion and for what I want to tell you, it's important to notice this averaging with the weight may also be considered as the average over a random step. So we introduce the random variable y, which is the distribution W, and then, which is the weight, and then the average value of the density is the value of the density, which is, so to say, came to point X from the different points X minus Y, and the probability of such coming is determined by the density, which is W. So the weight averaging may be considered as the averaging over random step. And what is not reasonable, or what is the problematic on those operations? The first problem is that when you do such averaging, it's not enough just to do averaging. You should go through an asymptotic procedure. For example, if you average from the molecules to hydrodynamics, you should take such a volume on the coarser scale, which is much larger than a single molecule, that is, contains very many molecules, but much smaller than the volume which you consider on this large scale. This is called representative elementary volume, and it is introduced in this or that way in any averaging theory. For example, if you average in the porous medium, then you introduce the volume which contains very many pores, but so it is large compared to one pore, but still it is what is called material point on the Darcy scale. And it is more or less okay. It may be made strict if you have just one such average. But if you have several such asymptotic transitions, like, for example, several volumes in the porous, several scales in the porous medium, then it is much more difficult to substantiate, and you get a lot of values that tend to zero and to infinity simultaneously, and you have to speculate about one infinity larger than another infinity, and it is not something which is mathematically strict. And it often leads to order of magnitude considerations which may be different. What is even worse, it may lead to the different results, to the different averaged equations on the macro scale, or to the different averaged coefficients. And at least it is not proven in any way that those coefficients are the same. And it makes a usual physical question about what I would call objectiveness of the theory. I mean, we have a mathematical theory that describes flows on the macro scale. We know that the theory is not unique, but the nature is unique. So apparently we have to select the right, I put it in quotes, the right theory out of many ones, and we do not know which one is right. So this causes some even philosophical problems. There were some physical philosophical study of what is called multiple descriptions. But I will not go into the detail, but just to mention that it may be a problem. So what I tried to develop instead is the method which refuses from asymptotics. Well, it may be introduced, but I do not use it directly. And this is the method which I would call, which I call continuous upscaling. Now I transfer to explanation of this new method. And again, I will have to go not to go to the details. So if something is unclear, please stop me and ask questions. I will start with an example, and this example is the map of the campus of my university, DTU. Yao knows that we all sit in the point 1 in the campus. Yes?
Yes.
Yes, but what I would like to draw your attention is the little number on the lower right corner of this map. It is 200 meters, yes? So what does it mean? It means that one unit of the map contains 200 meters. So this is the scale. We can take larger scale and even larger scale. So what will happen is that this number will change. So we can introduce the measure of the scale. I call it alpha throughout the presentation. So for the first map, it is 1 to 200, then 1 to 500, and up to 1 to 2000. So this is the scale parameter which is used in normal maps and probably in normal ways of averaging to some extent. By some reason, it is convenient to introduce the scale parameter S, which is logarithm alpha. So S increases from a fine scale to coarse scale. So it will be logarithm of 200 and it will be logarithm of 2000. So the difference is approximately 3. So what happens when we transit along the scale axis? Actually, there are two things that happen. The first thing I would call is scaling. So the points which denotes the same physical points become closer to each other, but nothing else is changing. So scaling is one kind of operation. But if you look into the map carefully, you will see that also some details disappear when you transit to the coarsest scale. And this is due to averaging. What is averaging? It is when several points on the finer scale become glued in one point on the coarser scale. So the map makes sort of averaging or sort of smoothed with some weight which the people who make maps do not report to us. Actually, maps are a little bit tricky thing. The people are cheating a little bit and they make continuous scaling but discrete averaging. But you can do it if you experiment with the Google Maps. You can see it. So we have to combine the two operations of scaling and averaging. The next idea is to make the axis S continuous. So we can transit not between 1 200 to 1 500, but we can transit to all the intermediate scale. And we have to design the continuous mathematical operation that would make this continuous transition. So we have averaging, which is average over the random variable. We have scaling, which is, if you work about density, you multiply the axis and the value of the density by the same number. You may combine them. It turns out that if you make scaling first and averaging second, or averaging first and scaling second, you get different results. But this difference disappears if you use small transition between the scales. What does it mean, small transition? It means that this y averaging variable is small, your weight is concentrated over a small neighborhood, and it means that this alpha scaling factor is close to 1. So you can make sort of expansion. You represent 1 divided by alpha in terms of exponent of S. S is the scaling parameter, and represented as 1 plus S, where S is small. You expand M with regard to Y up to the second order. It may be explained why, but I will not stop on the detail. And if after some manipulations, you get you get a differential equation, you get a differential equation which looks like this. Your density now depends on the scale, and it obeys the second order differential equation in which you have the two terms. As I will explain later, the first term is responsible for scaling or for transition to the smaller scale. And the second term is responsible for averaging, and it is similar to sort of diffusion. And you know that diffusion is responsible for smoothing. And the diffusion coefficient or smoothing coefficient is the average value of the square of variable y divided by two steps by scale. And this is known to everybody who studied, for example, in Einstein theory of Brownian motion. It is very similar to Einstein's derivation of the equation for Brownian motion, and that is the equation of diffusion. The only difference is that in the Einstein derivation, S was time, and here S is the scaling parameter. So the density moves along the scale in a way of diffusion. You may say that this derivation is not strict because it includes expansion, and it is very difficult to understand why we should, for example, expand M up to the second order and not up to the third. And vice versa, why we expand exponent up to the first order. Fortunately, there exists a mathematical theory. It is the theory of what is called continuous time or continuous Markov processes, which makes it possible to make it absolutely strict, and what is more important, it makes it unique. So what is the idea of the theory? We consider upscaling as a transition operator between the scale. So we do not specify what kind of operator it is, what kind of operation it is. So we take density and we apply operation. And we require just the two things. One thing is that the transition between scales 1 and 3 can be done through the intermediate scale 2, and it should be done in such a way that it should be independent on the intermediate scale. So if we want to jump from scale 1 and 3 directly, or we want to jump it through the scale 2, or we want to go from 1 to 3 through any number of intermediate scale, we should obtain the same result. By the way, this rule does not work if we take maps, for example, from Google. They do it differently. And the second principle which should be obeyed is that when we transit between the scale, the separate points should not jump far away. If I stay at point 1 on the scale, on the fine scale, then on the coarse scale, this point still should be approximately in the same place. It should not jump. And this means that the transition between the scale should be continuous. So those two rules, composition rule and continuous transition, immediately results in what is called continuous theory of Markov processes. And then it results at the end in the same transition equation responsible for scaling and averaging. There is also displacement coefficient, but it does not play any role. So the only coefficient which is non-unique is the degree of averaging per scale. And this equation, again, if you know the theory, this equation is somehow generalized equation of what is called Ornstein-Uhlenbeck process. I mentioned this word just to say that it is very well studied, the solutions are known, and you can manipulate with this equation pretty easily. So this is the equation for upscaling of the densities. But now the next problem comes, and this is the problem that we do not, if we talk not about the map, but we talk about the transformation or motion of the physical values, we do not have to upscale only densities, but also we have to upscale many other values. And I mentioned, well, in order to explain, I just take the standard system of equations, of flow equations, which consists of mass balance, concentration balance or additive balance, momentum, and energy equations. Well, I just take it as an example for illustration. Any modification is possible. But this is just to show that this equation, this system contains several typical values. The first value is density. That is the amount per unit volume. This amount is what in mathematics is called a measure, is the density of a measure. And measure is something like may be added if you consider it at different points. For example, the density is the density of a mass. And if you take the two volumes, then the masses should be added. So density of some additive measure in the space. Concentration is the measure of partial amount of some additive to the mixture. Then we have the density of momentum, the density of energy. All those are the same type of values for which we have already derived the upscaling equation. But now we have fluxes. And fluxes are different kind of values. They are not additive. They actually are additive over the surfaces of the space. So the fluxes are different kind of mathematical values. And finally, we get sources. Sources are more or less derivatives of the densities with regard of the time, but still it is a different kind of values. So if we consider the general transport equation, we have densities, we have fluxes, and we have production terms of or sources which we have to derive the upscaling laws in principle. I will not explain it in general, but I will just explain it for one equation, which is the diffusion equation. What we have to do. The diffusion equation contains, first of all, concentration. And concentration is a density, so it should be upscaled as the density. Then it contains the flux. The flux should be upscaled in such a way that the form of the equation is preserved. If we have the flux, diffusional flux, then depending on the scale, the form of the diffusion equation should be the diffusion equation. And it may be shown, it is a theorem, that the fluxes should be upscaled by the same rules as a density. But now we have sources and we have gradient of concentration, which enters the, sorry, I have very sensitive mouse. We have gradient of concentrations. which are derivatives of the densities. And my work, one of my works, which has been done, I will not bring it here, it is complex equations. There are rules for upscaling of the derivatives. And finally, we have, after we upscale derivatives, so we have the equation for the diffusion flux, which is the diffusion flux is a product of diffusion coefficient and concentration. So we know how to upscale the diffusion flux. We know now how to upscale the gradient of concentration as a derivative of the density. And from these two equations, we can extract the rule for upscaling of the diffusion coefficients. And it is not always simple, and these rules may be different, as I will show in the next step. So, just as an example, I will show you how the diffusion coefficient is upscaled. So, what is the idea? What do we expect from diffusion coefficient to look like when it is upscaled? We have this axis of scales S. We have the diffusion coefficient on the original axis, which is some inhomogeneous function of x of the position. So we consider diffusion in inhomogeneous medium. If we come to a coarser scale, then first of all, the oscillations should become on a smaller period because we scale the axis. And second, the oscillations should become smaller, because we average. So we should expect something like this. Then on the even coarser scale, we should expect even less oscillation. And if we go in principle to infinity, we have a constant, at infinity constant value of the diffusion coefficient. So if you plot it, you see something, if you plot it as a surface, you see something like this. You have axis x, you have a bihorizontal axis, you have the axis of scale vertical axis, and the diffusion coefficient oscillates along axis x, but those oscillations becomes more frequent. They decrease in size until it becomes constant. So this is the picture which you more or less expect to see. Now, how it looks in terms of equations. I will upscale the convective diffusion equation with diffusion depending on the scale and source term also depending on the scale, also oscillating. The velocity will be considered to be constant. It may be shown that for incompressible flow, the velocity will be just constant. No reason to make it oscillating. And it turns out that the equation for upscaling the diffusion coefficient is different depending on what you take into account. If you just consider pure diffusion, no convective term, not density, no source, then it may be shown that inverse value of diffusion coefficient is upscaled like density. Not the diffusion coefficient itself, but inverse value to the diffusion coefficient. Then the upscaling picture looks like this on the plot on this page. It is numerical calculation for the different initial condition. The upper plot is when the oscillation on the initial scale is relatively smooth. On the lower plot, it is stepwise. What is interesting is that the the decrease of diffusion coefficient with the scale is not very uniform. First, it decreases slowly, but after a while, it starts decreasing faster. And this is due to the fact that we upscale inverse diffusion coefficient. So we talk about not arithmetic averages, but harmonic averages. And it may be shown that at the limit of infinite upscaling, infinite scale or scale S, then the diffusion coefficient tends to harmonic average of the upscale diffusion coefficient, or of the initial diffusion, sorry, of the initial diffusion coefficient. So actually the harmonic average is preserved under such upscaling. Then when we get external source, it turns out that immediately the situation becomes more difficult. You have to introduce the flux, and the flux is not uniform because you have the source which adds or removes the substance from the system. And then you have two upscaling equations, one for the flux itself and one for the flux divided by diffusion coefficient. So instead of one upscaling equations, you have to solve two of them, and they cannot be separated, or at least I found the way of upscaling. And then the flux divided by diffusion coefficient tends to harmonic average of the initial values. And the flux tends to the arithmetic average of the initial flux. So you see that the picture of upscaling becomes more difficult. The plots are similar, but still it is a different kind of equations. And the final equation, well, I will finish in 3-4 minutes. I hope that it's in time. The final equation that I consider it is the diffusion with convection. And it turns out that the convective term adds some additional term to the upscaling equation for diffusion. And this is a nonlinear term, including quadratic diffusion coefficient. It may be demonstrated, although in this case I could do it only numerically. In the previous cases, it was proven. In this case, it's only numerical proof that the harmonic average of diffusion coefficient still tends to the harmonic initial average of the diffusion coefficient. So the diffusion coefficient tends to constant. But what is interesting is that it is not true about the solution. In the previous cases, the solution tended, in this case and in this case, the solution concentration tended also to the constant. But in this case, the solution does not tend to a constant. It actually continues oscillating, and the oscillations grow as you converge to the coarser scale. So in strictly mathematically, there is no limit. And this may be proven. So in this case, we have paradoxical situation where we can average the diffusion coefficient, but we cannot average the solution. So the problem does not have the problem of averaging or upscaling cannot be fully resolved. So this is what I want, well, this is how the diffusion coefficient converges to the average value. You see that in this case, the convergence is slower. It's also interesting that we have the effect of upscaling. So first, the oscillations become more frequent, but then they are also moved to the right, and this is due to the contribution of velocity. The fact that the fluid moves all the picture with the velocity. So that's why the upscaling diffusion coefficient start moving to the right. So, okay, that's all I wanted to tell you today. Now the conclusions. So the theory of continuous upscaling has been developed, and it has been developed, which means that the general rules have been obtained. The uniqueness has been proven. The rules for upscaling of densities, fluxes, and actually non-convective fluxes, velocities, and other values have been developed. Also sources. And then we applied the theory to diffusion coefficients. And it has been proven that the results depend on in what, let us say, additional terms in the diffusion equation we consider. And the asymptotic behavior may be rather non-trivial, depending, for example, for the convective case, the diffusion coefficient converges asymptotically to some average, but the concentration does not. So this is all I wanted to tell you today. The work is continuing now, but since I work practically alone, that it is going slower, then I would like to show if somebody got interested, we could discuss about possible continuation. And so thank you very much for listening, and it is time for questions. Thank you.
Okay, thanks very much for the nice talk from Alexander. So that's are there any questions so far?
Yes.
Yeah, Diana?
I wonder does it work better or worse if you have clear separations of length scales, or compared to sort of a continuum of length scales in the problem?
Björn, first of all, I am very glad to hear you. Yes, I think. Well, I'm sorry that I do not see you. Yes.
Do not see.
We're in Oslo.
Oh,
Yeah.
Oslo. We're here from Oslo. Yeah, Fiona is talking.
Yeah, I'm up at. Well.
Yeah. Where are you?
Of the screen.
Yeah.
Yeah.
There.
Yeah.
There I am. So. Yeah, I
Well,
wonder.
if you have clear separation of the scales.
Yeah.
I would say, well, for clear separation of the scales, it is mathematically more difficult, but still easier than if you make VAT. But for me, it is the question, what does it mean, clear separation of the scales? Do you have it in the nature, so to say? Or in the nature, we always have continuous change of the scales. And here I do not know the answer. If you have an idea, please tell me. I mean, you can, well, if we talk in terms of equations, yes? You can take, for example, this diffusion equation.
Yeah.
Take the scale S1, specify the diffusion coefficient, on this picture. Yes? Specify the diffusion coefficient at scale S1. Sorry, my mouse is jumping. Specify the diffusion coefficient at scale S1. Solve it numerically or analytically until scale S2, and find the diffusion coefficient on scale S2. No problem with that. It's easy to solve. So it works. Yes?
Yeah, Fiona?
Thank you.
Thank you.
Diana, you have questions?
Hello.
Can I ask you a question, please?
Yes.
I'm sorry, I do not have a camera on my computer, so that's why you don't see my picture. Thank you for a very interesting talk. You had the 4 balance equations on one of your early slides. I was wondering what happens to the entropy during the upscaling. You could add a 5th balance equation for the entropy. Obviously, when you do the upscaling, you lose entropy in the system. But what happens? Can you describe that in a similar set of equations?
Thank you for asking that. Entropy is a density, so it should in principle be upscaled as a density. But I will not hide from you that I'm struggling now with the values which have, so to say, double meaning. And even before entropy, I would like to talk about pressure. Because pressure, from the point of view of those equations, pressure is non-convective flux, yes, of momentum. So the equation for upscaling non-convective fluxes can be derived. You take convective flux, you subtract the part depending on density velocity, you get the equation for upscaling of non-convective fluxes. But on the other hand, as you know from thermodynamics, pressure is a variable, for example, in the equation of state. Yes? So density depends on pressure. And it is equation of state. So it plays sort of 2 different rules in different equations. And it may be shown that if you upscale it, you get different results as a part of the EOS or as a part of the flux. And to be honest, I have not invented yet what to do in such cases. The only case which I consider it until now is the momentum. Momentum is the convective flux for density, but it is the density for the momentum. So it is both convective flux and density. For such cases, it can be, for this case, it can be shown that it is upscaled in both cases in the same way. But I'm afraid, regarding your question, that if I will start upscaling entropy as a density, then some kind of such contradiction will come, and the entropy will have to upscale in 2 different ways, which might mean then on the coarse scale, you have additional contributions to entropy because of the averaging, which is not that stupid. So.
Okay, thank you. I have another question, if I may.
Yes,
when you do the continuous upscaling, suppose you have a system like a reservoir, for example, and in this reservoir contains a fairly homogeneous sandstone, for example, and then it has fractures. So at some point, when you do the upscaling, you all of a sudden hit a drastic change in the physical properties of the system. How is that handled?
If you look into my second paper, I upscaled the diffusion equation, but you know that it is similar to the flow equation in the reservoir, exactly for the case of fractured porous medium. I just opened the first slide. It is chemical engineering science of 2022. In this case, fractures are getting slowly disappearing, but at one point, well, I refer to probably to this plot. Yeah, to this plot, for example. In this case, what happens is that the fractures are getting smoothed out, but after some scale, they sort of disappear and you have uniform picture. So, and if you, well, I suppose you know how the science in this case is, and you know that people divide such reservoirs into what they call single porosity and double porosity. So you may say that what happens in this picture, for example, at scale 1.5, it is double porosity medium, because because the picture is smooth, but you still have visible fractures. But if you smooth it so much as to the scale 3, you get a single porosity picture. So
yeah, but that would have a dramatic effect on the flow properties, wouldn't it?
It has a dramatic effect on our modeling of the flow properties. I would put it like this.
Okay.
Yeah, well, yes, if we smooth too much, we get a smooth model.
Okay, thank you.
You're welcome. Okay. Yao, I do not hear more questions or see it in the chat. Can you hear me? I do not hear the porlap. This mic is.
Yeah, sorry.
Yeah, I hear you now.
Yeah. We don't have more questions in the chat. Yeah. Are there more questions from the audience? No. No. If not, let's thanks Alexander's nice talk again. Yeah.
Okay, thank you very much for listening, and I will be happy to share the presentation.
Yeah. I guess more questions may come afterwards. We'll also upload this talk to the YouTube channel, so maybe persons will see it and ask more questions from you.
Yeah, and Yao knows how to find me.
Yeah, sure.
Yeah, okay.
Thanks, Anthony.
Thank you.
What's your master's degree?
Yeah.
Nice.
Also my big studies, semester students.
Okay, I'm leaving the meeting. Thank you, everybody, for coming.
Yeah, thank you too.
Thank you.
Very friendly sites.
Yeah.